I'm Spencer. I'm a PhD student here at Monash University. I'm going to be talking about a project I've just started working on the direct inference of neutron star equation of state gravitational waves. So that's a bit of a mouthful. Let's start right at the beginning with stuff I'm sure you all know. What are gravitational waves? Gravitational waves are ripples in space-time that are caused by compact binary mergers, or at least the most common source is compact binary mergers, things like binary black holes, binary neutron stars, and neutron star black hole mergers. So as I said, these generate ripples in space-time that we can detect here on Earth. There's a nice plot in the bottom right-hand corner of what this looks like. So we have this thing known as a strain, which is really just a contraction in space. And as you can see, as they start merging, it starts out slow, and then eventually we reach a peak and increase in frequency. And then finally, there's a merger. At the merger, there's a ring down as it dissipates off. So for this talk, I'm going to be focusing mostly on binary neutron star mergers. So I covered this a little bit in the previous slide on detecting gravitational waves, but the basic idea is that we use large lasers, large interferometers. They're about 4 kilometers long, and they measure the stretching and squeezing of space-time in quantity known as strain. So here's a picture of my favorite and the best interferometer, if anyone wants to argue with me. Livingston, which is in the US, in Louisiana, in a swamp. There's also some photos of me at the observatory when I visited last year. So there's 4 of these detectors operating around the globe. As I mentioned, Livingston in the US, Hanford, which is also in the US on a nuclear waste site, Virgo in Italy, and Kagari in Japan. Okay, so onto neutron stars now. I'm sure everyone has at least a rudimentary understanding of what neutron stars are. I'll just go through a little bit of background. So they were theorized back in the 30s. And then discovered in the 60s by Jocelyn Bell as pulsars. I'm sure we all know they're formed during the death of massive stars in supernovae. What's really interesting about neutron stars is they're extremely dense. You have about 1.4 solar masses squeezed into about 12 kilometers of radius. And because they're really dense, they have these interesting composition in terms of equation of state and nuclear physics. And this is really unknown. This is something we'd like to probe. So on now to equation of state. As I mentioned, it's not well known. What an equation of state really is, to give you a high-level overview, it's a representation between pressure and density. So it tells you how, for a small change in pressure, for a small change in density, what change in pressure do I get? And it's typically given as one of these plots like this. These plots come from complicated nuclear physics models that I don't understand, but you can read the papers, some of them listed there if you're interested. And of course, what we'd like to do as theorists is parameterize these. So the way that we do this is we consider the equation of state to be a polytrope, or polytropic fluid, which is represented by that P equals K rho to the gamma there. So all this is really saying is your pressure is equal to your density to the power of some adiabatic indice. And typically, if you want to describe things well, you need to use a piecewise combination of polytropes or a spectral model. So I'm going to be talking about piecewise, but there are other models. Indeed, there are non-parametric models that are better. Okay, so once we have the equation of state, that doesn't really tell us much about the neutron star composition. To find out things like mass and radius, we need to solve the equation of state. And the way we do this is we use something known as the Tolman-Oppenheimer-Volkov equation, TOV equations. So I have a schematic diagram of this on the right-hand side. So you essentially take your pressure versus density diagram, you pass it through Robert Oppenheimer, and you get out your mass radius curves. You also get this quantity known as tidal deformability, which is a measure of how easily a star is tidally deformed when subjected to an external field. So a larger tidal deformability corresponds to a larger, less compact star that is easier to deform. And the unfortunate thing about this is there aren't analytical solutions aside from the trivial case, and it's slow. It has to be done numerically. All right, so I mentioned before, we want to do this with gravitational waves. How is this actually done with gravitational waves? I have a really simplified view of gravitational wave phase here. So if you imagine the phase of the signal, it's broken up into a point particle component and a tidal component. So the point particle component is if there was no tidal deformability, if you imagine two black holes merging, and there's a tidal component added on by the neutron stars. So to measure this, what we do is we measure a change in phase induced by the tidal components, really a departure from the point particle. And this tells us about tidal deformability and therefore the equation of state of the neutron star. Okay, so in practice, this is done using Bayesian inference. In particular, what I'm going to be talking about and what certainly most of the LSC uses is Bilby, which is a code developed here at Monash. Shameless plug for everyone. And this is, Sabrina mentioned it earlier in her talk today. This performs Bayesian inference and lets us measure tidal deformability and mass for binary neutron star, along with a lot of other things. However, if we want to directly infer the equation of state parameters, so this parameterized version, this piecewise polytrope, that would involve numerically solving the TOV equation many times, and that's too slow. So typically this is done using a form of hierarchical inference. So that really brings me to my work that I've just started developing, which is a machine learning model for EOS inference. It's something I'm calling the Militov solver. So the idea is to replace numerical solutions of the TOV equation with a machine learning model. So again, for those of you who are visual learners, you take in, you want to consider it a black box, you take in a mass and polytropic indexes, sorry, I should say adiabatic indexes, into the Militov model, and then it spits out a tidal deformability. And this is a really fast process, which means it can be done during the Bayesian inference. Right, so let's look at some preliminary results. This is the model applied to a GW170817-like injection. For those of you not familiar with gravitational wave phone numbers, this is the first and the best binary neutron star merger. Have any 1904-25 fans in the room? Oh, just a bunch of contrarians. Anyway, so this is kind of an idealized injection of this event. I've simplified, rather than doing full model, we've simplified the equation of state to just consist of a single adiabatic index. So rather than having 3 or more polytropic indexes, I should say adiabatic indexes. And I've also simplified things to just sample over mass, tidal parameters, and EOS parameters. It's fantastic. Okay, so yeah, you can see, trying to explain corner plots. Essentially, forget about everything else and just focus on this plot over here on the bottom right-hand corner, which shows, the orange line shows our injected value of our adiabatic index, and the blue line is the recovered posterior distribution. So we can see that we recover the adiabatic index well. All right, I'm going to skip over this really quickly. So the motivation for doing this really is gravitational wave cosmology, which is the idea of performing cosmology, particular Hubble parameter measurements using gravitational wave events. And it should be a cosmic distance ladder independent measurement of H0. And it's been proposed as a possible solution for Hubble tension, but as you can see from this nice plot from Rachel Gray, fortunately at the moment it sits right in the middle between Planck and Shoes. So the general idea is that with these events, with this equation of state solver, we can break a mass redshift degeneracy. And this allows us to determine a redshift for the event. And since we have a luminosity distance intrinsically encoded into the gravitational wave source, and we now have a redshift, we can obtain a posterior on H0. So I will leave you with my summary slide. Thank you all for listening.
When you're trying to do this, you've got to have quite a good model of what the signals should look like depending on the equation state, right?
Yeah.
So when you get those, I'm familiar.
So it's actually, the idea is that you get a, when you're generating the waveform for this, it's dependent on lambda. So really what you're doing is you're passing in, go back, slide. So you generate, we can have a chat about this later when you do the sampling, but yeah, you generate a lambda from your mass and your equation of state parameters, and that gets fed into the waveform.
Okay, I see. Yeah.
So that gamma you put in is a vector, right? It's like piecewise.
Yes, it wasn't in the model. It should be in if you want to do things properly, but in the example I showed, it was just a single index. Yeah.
So the question about exactly so you run, or someone else runs general relativistic simulations of Newton's measures of the emergent phase?
No, it's even simpler than that. Just TOV equation.
So you have just the equations of piecewise polytropes describing different regimes of
yeah, and then I solve the TOV equation 100,000 times for different polytropes. And then that gives me a bunch of lambdas.
Okay, then you have that data for different patterns of Newton class and different regimes of gamma.
Yeah,
you get different lambdas and
exactly. Yeah,
two to one mapping, two progressive variables and one target variables.
Yeah,
and then for the bill-based study, you actually have a gravitational waveform which is characterized in some way by some lambda.
Yeah, that's correct.
And then you use it to infer M and gamma.
Yeah,
okay.
Yeah.